All right, well, g'day people. Tonight we're going to hear from Dr. Bhavik, Harish, Lodhia, who's recently come to Australia from the UK. So we're giving him a baptism of fire tonight. I'll just go through some of the housekeeping first of all. So just want to thank our corporate members, High Size, Southern Geoscience, Total Seismic, Bell Size, Transparent Earth Geophysics, Santos and DUG. And also thanks to our branch sponsors, which for New South Wales is GBG Australia. Housekeeping and Zoom etiquette. If you have a question, just go and click on the Q&A function, as you can see on this screen, and type your question down the bottom there. There's a lot of benefits to being an ASEG member, and I'm not going to go through them all, but seeing this tonight is definitely one of them. Okay, and you can keep in touch with the ASEG via Facebook, Twitter, LinkedIn, and also YouTube. Also a shout out for the AEGC, which is coming up in September in Brisbane. Hope to see you all there. Okay. So just a little bit about Bhavik. He's just moved to Australia from the United Kingdom, and he's currently doing a postdoctoral fellowship in energy technology and geophysics at the University of New South Wales. He graduated with a PhD in geology and geophysics from Imperial College in 2019 and completed a master's bachelor's degree in earth science at St Anne's College at Oxford in 2014. And his work is focused on basin dynamics, geodynamics, sediment source to sink, and petroleum systems modeling. So welcome to Bhavik.
Hi there, so thanks for the introduction. I hope everyone can hear me, and thanks again everyone who's turned up in person and for everybody logged in online and listened to my talk. So the presentation today is focused on my PhD work that I completed at Imperial College London in 2019. I'm still involved in some collaborations with Imperial on using drainage inversion for various purposes. So hopefully this work will continue on into the future. So my work was focused on linking together different processes to do with sediment source to sink. So looking at a complete picture from continental uplift, geomorphology, sediment deposition, and tying them all together. So tying together what's going on onshore and offshore to both produce sediment and capture it within sedimentary basins. And I looked at a particular case study, which was the Mauritanian Basin, which is just offshore West Africa. So this was a relatively underexplored and understudied basin compared to other West African basins such as the Niger Delta and Angola. So this really was a pretty frontier basin compared to others. So just a quick outline of my talk today. I'll begin with a introduction to African dynamic topography and sedimentary flux around Africa. I will then discuss Mauritanian stratigraphy and sedimentary flux for my study area. I will then delve into the causes of subsidence from a geodynamic point of view, and then tie this to regional uplift modeling from the perspective of continental drainage analysis. And then I will finish the presentation by explaining a methodology in which we can predict sedimentary flux offshore by looking at what the rivers onshore can tell us. So the two figures on the screen you can see here on panel A and B both, of course, show Africa and the major river systems within Africa. The panel on the left, so panel A, shows the topography onshore, and offshore is a global grid of offshore sediment thicknesses. And as we can see, as expected, we see these big, thick piles of sediment located immediately adjacent to the major river systems across the continent, which is as to be expected. However, when we view this alongside continental dynamic topography, which we can see on panel B, what's quite striking is that a lot of these river systems, in particular the Senegal and the Niger, are actually located in dynamic topography highs. So these are areas of known uplift within the last 30 million years. And in the case of Africa, there is a regional event known as the African superswell, which has uplifted the southern half of the continent during the last 30 million years. So this begs the question, are the two processes linked? Can we find a link between continental uplift onshore, and sediment deposition offshore? And if so, this could be a potential way to predict the presence of reservoirs in the offshore domain by looking at what is going on onshore, especially around passive margins. So in terms of the data that I had, to be perfectly honest, there was not very much. As I mentioned, the Mauritanian Basin is a very underexplored basin compared to others. So the panel on the panel you can see here shows the region of the 2D seismic data that I had. The sediment thickness you can see on the screen here is from the global compilation from Whitaker 2013. However, I've overlaid on the positions of the wells that I had access to, labeled from A to H, and there were only 8. So this is not one of those studies where I was fortunate enough to have access to hundreds or potentially 1,000 wells. There was literally just 8 wells for quite a large area. However, that was enough in the end. And then I was very fortunate to have one long seismic line, which I will show later in the presentation, the position of which is on the screen here.
So we can't see some of it.
Oh, I didn't know that was actually big. Sure, let me. Can I hide that? Oh yeah, there we go. That's fine. Okay, so there, yeah, you can see the position of the 8 wells. The gray circles are positions of salt dipiers as mapped on the seismic data. So we can see that there's a lot of salt towards the center of the basin, closer to the shore. The black line here, the 2 dashed lines here mark the continental ocean boundary as viewed on the seismic data. And in total, there are 53,000 line kilometers of 2D data, 8 commercial wells. The wells had check shot data, and I was fortunate enough to have access to some high resolution biostratigraphy from these wells. So this figure here is the long seismic line, which the position of which was shown in the previous slide. So both of these figures, the top and the bottom, are the same seismic line. Panels C and D are a zoom of the near shore part of the long line. So as we can see, this is actually a beautiful line. The moho is pretty clear, where we can see the transition between continent and ocean. And what we can see here is the interpretations are shown in panels B and D. There were 7 horizons and the basement. The basement horizon and the horizon above that, which is quite prominent vector, are not penetrated by any wells along the margin. However, the rest of the horizons were. And we can see this big, thick sediment package from the seabed down to the Pliocene. And that horizon is dated at 5.6 million years. And then another package which goes to the base Miocene. And these occur at the top of these salt domes. which you can see. So that was really the first indication as to, well, raise the first questions as to how did this occur, why did this happen, and there have been several discoveries within these intervals now within the Mauritania region, where quite prolific reservoirs have been found. So the million-dollar question was, can we find a link between the deposition of these reservoirs and onshore processes? So the first thing I did was I mapped all of the seismic data across the region, and then calculated the isopacks between those. So and calculated the solid sedimentary flux history from those isopacks. So the panels you can see on the screen now from A to F are the corrected sediment volumes between each of those horizons on the figures previously. So those two packages which I mentioned in the previous slide, from the present day to the base Pliocene, and then from the base Pliocene to the base Miocene, we can see quite thick sedimentary packages deposited within these time intervals. And what's quite striking is within the Miocene, most of that sediment is concentrated within the center of the basin. So something must have happened in order to produce that. Panels C and D are where you see the high sediment accumulation is predominantly carbonate deposition, which is confirmed by the well data. So this big thickness here is a carbonate platform that was deposited then. But really, it's this interval here, this relatively shallow area of high clastic sedimentation that we're interested in. So we can see a low sedimentary flux from Cretaceous times to Neogene times. The Neogene increase in sedimentary flux is concentrated in the center of the basin during the Miocene, and then occurs across the basin towards present day. So that's here. And there's a significant increase in sedimentation from Pliocene times to recent times, as you can see here. So in terms of stratigraphy, so this was a figure that I produced to summarize the tectonic history and the stratigraphy of the region. We can see those packages here. So we can see these packages of plastic sedimentation across the basin, increasing at these times. So as I mentioned earlier, there are known reservoirs within, which is marked by the letter R in these circles here, that are intersected within Miocene to recent sandstones across the basin, particularly within the Chinguetti field in Mauritania. And these clastic sediments are predominantly sourced from onshore drainage systems, the most prominent one being the Senegal River, which is located immediately adjacent on the continental passive margin of Mauritania. So from the seismic data, we can see that salt movement ceased at the base Miocene. So whatever subsidence occurred to produce the accommodation space required to capture these sediments cannot be explained by that. There's no major faulting or anything like that within this region, which is visible in the seismic data at least, so that can't be an explanation. So this raises further questions as to how was the accommodation created to capture the clastic sediments which are in the basin. So it really only left one option or one possibility, which was there must be something geodynamic happening, something that's actually pulling the crust down to create the space required to capture these sediments. So that raised the first question, and this originally wasn't part of the PhD, but then it was just one of those sort of off ideas that led into much more. So I decided to look at this further. And before I go on to that, so this is just a figure that plots those values from the isopacks I showed earlier, but on a graph. So we can see that the period of increased sediment flux here in the green box. Although this figure is somewhat deceptive, although there's only a tiny step here from the figures I showed you earlier. The majority of that is located within one small geographic region, so it is still represents quite a significant change sedimentation. The black circles here are data points from another study that was conducted onshore the West Africa around the Niger Delta, and it also corresponds with this pattern of increasing sediment flux during the last 30 million years, which we're also seeing in offshore here. So the first thing I did was I backstripped each of these wells to actually calculate the subsidence history. And what we can see is actually quite striking. So for the wells in the center of the basin, the subsidence, the periods of increased subsidence are marked by the red boxes here. We can see that there is between 0.4 to 0.8 kilometers of subsidence within the last 30 million years, which is significant. You know, it explains why these sediments were captured, but not how it doesn't explain the mechanism behind it. But at least now we can put a number onto what the subsidence is just by backstripping the wells. So in order to explain this, the only other sort of alternative, or the only possibility after we could rule out soil movement and tectonics and faulting was looking at geodynamics. So we looked at the shear wave tomography of the region. So this figure here shows a slice at 150 kilometers. So the colors represent shear wave tomographic speeds. So the hot colors, so red, are slower speeds, and the cold colors, blues, are faster speeds. So for those of you who aren't familiar with shear wave tomography, it can be used as a proxy for temperatures within the mantle, whereby the less rigid rocks are, the slower the shear wave tomographic speeds will be, or the lower the speed of which tomographic waves will propagate through them, which is correct, will be, and the more rigid they are. So if they're colder, shear waves will travel faster through them. So this can be used as a proxy to gauge what's going on in terms of temperature within the mantle. So looking at this depth slice at 150 kilometers, what we can see is quite striking. There's a protuberance of fast velocities that pretty much capture exclusively the Mauritanian Basin, where we're seeing all of this subsidence. And this is not seen north of the basin or south of the basin. And this position here, yeah, you can see my cursor, is a known magmatic hotspot, which is the Cape Verde Islands. So this is a mantle plume that is completely separate to all of this. And a lot of work has been done on studying that area of volcanism. But immediately adjacent to that, in between Cape Verde and the African mainland, we're seeing this big protuberance of fast velocities, which indicates that there's something going on within the mantle, which is reducing the temperatures, or there's an area of cold mantle pulling the crust downwards. So we updated the shear wave tomographic model, which was produced by one of the collaborators on the project, Stuart Fishwick at the University of Leicester, to include data from recent experiments and passive source seismic data that was acquired across Africa. Yep, so this just summarizes what I just mentioned. And we can turn these shear wave tomographic anomalies into temperature anomalies by just essentially using a lookup chart of values, which converts one to the other. So there were two methodologies we used for this. One was a mineral physics approach, and another was an empirical approach. And those are both published in these two papers by Goes et al. 2012 and Priestley Mackenzie 2006. So this is the methodology that we use to turn shear wave tomography into temperature to look at this region of the mantle. Yeah, so this indicates that there could potentially be mantle drawdown beneath the basin that's pulling the crust down. So putting all of this together in a three-dimensional picture, so this you may have seen on the advert for this talk. These two panels here show the shear wave tomographic speeds. The two dotted lines show the depth to the 1330-degree isotherm within the mantle as calculated using those two models which I described in the previous slide. And this is also plotted with the region, with the seismic data that I showed earlier, and also the position of some of the major wells. So here we can see the Cape Verde Islands, beneath which there is a mantle plume, as we'd expect, a big area of slow velocities. But then we can see this isotherm being drawn down by up to 150 kilometers below the Mauritanian Basin compared to its position beneath Cape Verde. So this strongly indicates that mantle drawdown is occurring right now at the present day, and probably is the cause for the subsidence that we can see when we backstrip the wells. So that would explain the process behind how this basin was created along a passive margin, where it's sort of a typical location which companies overlook when it comes to exploration. And another thing that supports this hypothesis is that residual ocean age depths decrease from Cape Verde to the towards the center of the Mauritanian Basin. So now to the next part of the talk. So everything explained so far indicates what's going on. I'll get rid of this. I just want to get rid of this black. Okay, I'll just leave it, and I'll just leave it then. So yeah, so we've looked at what's going on offshore. There's a basin, there's been subsidence caused by the mantle. There's a lot of sediment, great, but what processes onshore have produced that sediment? Because of course you can have subsidence offshore, but if there's no sediment source, then nothing will be deposited within the basin. So looking at rivers as recorders of uplift is one potential way of closing that loop. So the principle of this is that rivers capture the tectonic history and the history of vertical motion of the Earth's crust through time. So thinking of a river as a tape recorder of crustal movements. Looking at a plan view, so panel A here, you have a river that starts at a source somewhere up high in the mountains and finishes at some distance, which is called L here, at sea level. And if you plot elevation with distance, then you get a profile that in this synthetic example looks like this. And where these changes in gradient occur are known as nick points or nick zones. So every time there is uplift of the crust, that will cause incision and erosion at the river mouth, and that will lead to a nick point or nick zone. And those nick points and nick zones propagate upstream with time as rivers evolve, and you can assign a velocity to that. So this velocity is different to the shear wave tomographic velocities from the previous slides. So this is a nick point velocity. And the gray line shows the change in upstream drainage area, which of course increases as you get further away from the source of the river. It doesn't seem to. I don't want to click end. I think maybe if I click this and then this. No, I don't think it's. Open the Q&A and close it. Okay. Yeah, I'll answer that later, but no, that didn't seem to. I can crack on. Yeah. Fine. Yeah, no, it's okay. It's just. that might end. Yeah, but yeah, I'll crack on. Yeah. So looking at this idea as rivers as recorders of uplift. So I extracted just under 15,000 longitudinal river profiles from across continental Africa. Quality checked every single one of them to make sure that they exist, which took about a year of my PhD, just that. So that was so that was not a fun activity, but you know, I was at the end of it, I had a very good database that nobody had done before. People had extracted river profiles from Africa before, but on the scale of you know, 600 or 700, but not at this resolution. So this figure that you can see on the screen here shows the topography of Africa. As I mentioned, this region of high topography within the southern half of Africa, which is recent work is very supportive of the hypothesis that this is produced by mantle upwelling during the last 30 million years. So every river isn't actually shown here because there'd be too many and it would just black out the image. So every 10th river is shown. But what we can see is that the pattern of drainage at known magmatic swells, so those are labeled by the letters on the map. So this is the Hagar swell, this is the Tibesti swell, the Darfur Dome, the East African Rift Valley, Cameroon, and so on. We can see this dendritic tree-like pattern of drainage at these magmatic swells, which is the first indication that these rivers grew as the mantle was pushing the crust upwards in these, or raising topography in these regions. So we can take these river profiles and invert them to calculate the history of uplift. So I'll go through the process of that in the following slides. Well, actually, no, I start off with it here. Yeah. So the rate of change of elevation with respect to time, so that's this term here, del z by del t, is a function of two things: uplift, which varies as a function of space and time, and erosion. So this term here represents erosion, which varies as a function of space and time. So a lot of work has been done on this, which was not the focus of my PhD. So this is quite well established within the geomorphological community. This term here, this V0, is that nick point velocity that I mentioned in the previous slides. This AX is the upstream drainage area, which we can measure from these profiles. And that should be a Z, not an X up here. So that should be del Z by del X. Again, we can measure that from the drainage profiles because that's the rate of change of elevation with distance, which we get from the present day drainage profiles. And M and N are values which can be calculated by calibrating the model using real geological data. And what's great is we can integrate this term along the length of the river to predict sediment flux. So I'll come on to that towards the end of the presentation. And I did this for this region here in Senegal to test whether we can see the same pattern of sediment flux, looking at what's going on onshore and the data and results we have from offshore. Okay, so this is the equation that I mentioned earlier. So the rate of change of elevation with time is a function of uplift rate, which varies with space and time, minus erosion, which varies as a function of space and time. The erosive term can be modeled as a combination of calibration constant, nick point velocity, drainage area, and the gradient of the river profile, the elevation with respect to distance. And this shows all of the rivers now, all 14,700 from continental Africa. So by measuring this term here, we can allow uplift to vary as a function of space and time at each of these nodes, which are shown by the grid here, and calculate different uplift histories across Africa. And then by repeating this calculation and forward calculating the theoretical longitudinal river profiles, we can choose the model that has the lowest misfit between the river profiles which we see today and the theoretical river profiles calculated by an uplift rate history. So that is a method in which we can calculate the best fitting uplift rate history from an inverse perspective. So the figure here shows the actual data. So the black lines here are the longitudinal river profiles for the main drainage systems in Africa. And as we can see these for the largest rivers such as the Niger and the Nile, there were many tributaries along these, and we can see these big nick points where many tributaries join the main river system. And then for some of the smaller ones such as the Senegal, these are less pronounced, but they're still there. And again, we can see at the Congo as well. So these are the drainage profiles for the rivers I showed you in the last figure. And here are the drainage profiles, which are calculated from the best fitting regional uplift rate model, which are plotted in red. So as we can see, the fits are pretty good. There are some areas of misfit, such as here. I don't know if you'd be able to make out, but some of these profiles don't fit exactly. But in general, the fits are pretty good. The residual misfit was an average of 1.45, which is pretty low. So we can see that it is possible to extract reasonable drainage profiles from this modeling approach. So looking at this in a spatial perspective, so this black bar is blocking the top of this, but this panel here is at 30 million years. This is 25, this is 20. So these panels are at 5 million year intervals. And the figures here show cumulative uplift. So we're starting at 30 million years, which is sort of our base level. And then each panel shows how much uplift has cumulatively occurred since that time. And we can see that around Africa's dermal swells, uplift is growing, which is as expected. This is a lot of work supports this. And the values are consistent with independent geologic constraints, which I will have plotted up later, which I will show. And we can see a significant uplift within Eastern Africa and Southern Africa. So this is associated with that regional African superswell event that I mentioned earlier. And also between 1 and 3 kilometers of uplift between during the last 30 million years. So the figure here shows the locations of independent geologic constraints, which were used to calibrate the model. Now, if this was North America or Australia or Europe, there'll be thousands of points. But unfortunately, in the case of Africa, that data just does not exist. So really, there were only about 20 or 25 points from across the continent that were available to actually calibrate this model. So the fact that the fits are reasonable, even with so little data, was very surprising to us, to be honest, and very good news for my PhD. So yeah, most of the points are concentrated around the southern end of Africa because that's where the most research has been done. There's only a few points, 2 from the study region of this project, and a couple from Northern Africa and 1 in Eastern Africa. And then plotting these values against the predicted values, we can see that the predicted values and the observed uplift rate values are in a reasonably good agreement. They plot pretty close to a 1-to-1 line. So this is all just to support the robustness of this modeling approach. So looking at the region which I studied offshore, so the Mauritanian Basin, shown by the figure here. So the panel on the left just shows the nodes at which uplift was allowed to vary along. yeah, it shows the position of the nodes where uplift was allowed to vary as a function of space and time. The black lines are the rivers from within the Senegal drainage catchment, and the area of the Senegal drainage catchment is shown in the black dotted lines here. So here the scale is different to the previous figures. So the top end of the scale is 2 kilometers, and the lower end is at 0. So we can see that over the last 30 million years, there has been significant uplift within this region in the area of the Senegal drainage basin. So precisely, there's been between 0.5 to 1 kilometer of uplift within the hinterland of the Mauritanian Basin onshore. And this has been most pronounced during the last 10 million years and during the last 5 million years, where we see these thick packages being deposited offshore. So yeah, all of this uplift and of course associated erosion is concomitant with increased sediment deposition to the Mauritanian Basin. So I mentioned a few slides ago that it's possible to make a prediction of offshore sediment flux by integrating the erosive term along the length of the rivers. So just to explain that a bit better, I've got a video here. So this video here shows the results of a synthetic example of a river profile with a known uplift rate history. So I'll need to play it probably several times. So there's 2 phases of uplift here, one here and then a smaller period of uplift later on. And the panel here on the right shows the elevation profile, so the longitudinal profile. And as we can see, let's go back. This thing is in the way. There we go. So we can see this first nick zone here, which occurs, and then a second nick zone that occurs as a result of the second period of uplift. So, and the panel on the bottom here shows the cumulative uplift in kilometers for both of those. So as we can see, the 2 events that produce this river profile are reflected. So by doing this process in reverse and integrating the erosive term, we can calculate how much sediment was removed in order to produce this profile. So yeah, just wait for this to finish. So that's what I did for these rivers, for the uplift rate history that I showed in the previous slide. And these are the results. So the panel A shows just topography and the region of seismic data with the rivers plotted onshore just for context. Panel B is the offshore solid sedimentary flux as calculated from the isostatic mapping. So those are the same numbers as what were shown in the previous slides. And panel C and D are the results of integrating this erosive term along the length of the river profiles. And the difference between C and D is that the numbers have been averaged between the same intervals as the seismic horizons in panel D, just to give a comparison. So the very striking final result of this is that we see both offshore and a pattern of increased sedimentary flux as recorded by the stratigraphy, and the rivers onshore are also showing an increasing pattern of sedimentary flux. Sediments being produced by erosion due to dynamic uplift of the continental hinterland. So this was very striking because it shows that it is possible to predict patterns of offshore sedimentary flux by looking at, especially along passive margins, by looking at what's going on onshore and what the drainage can tell us. One thing is important to mention though is panel B. This is a volume flux, whereas this is a 2D flux, so this is in units of area, but the actual pattern of increasing sedimentary flux is consistent between what we're seeing onshore and what we're seeing offshore. So just to put this in, just to finish up and to put this into a regional perspective, so I think this is the last slide of the presentation. So the figure here that I plotted up shows a compilation of sedimentary flux values for each of the major African river systems. So the one for the Senegal is these are my results from the mapping that I did offshore, and the rest of these are all from these references at the bottom here. So as we can see, there's an increase in clastic flux at most African deltas from 30 million years to the present day, which is associated with this period of uplift associated with mantle upwelling. We see this uplift pretty strikingly just from the topography itself. I mean, the colors here is just present day topography. And we can clearly see that this is varies a lot from across Africa. This region of low topography here is the Congo Basin, which is an area of known mantle downwelling. So this raises a big question that are shallow mantle processes responsible for controlling the sediment budget to Africa's passive margins and potentially others around the world. So that was the final result of the PhD. I would love to have continued it, but then my time was up. So the results of this are published in a paper in Earth and Planetary Science Letters. So this paper covers the subsidence analysis and geodynamic work. A paper published in 2019 in JGR Earth Surface. This is more on the actual regarding the modeling approach for the inverse modeling, and has some more details on that. And then the final sort of source to sink paper came out at the end of 2019. I think in August 2019, yeah, which ties together the results of the uplift drainage analysis modeling and the sediment flux story. So yeah, that's it from me, and thanks to everybody for listening.
That was fantastic. We'll give this to you in a little bit, but in the meantime, does anyone have any questions in the room? Yeah, Barney?
Oh, yeah, just very interesting to see you putting together the onshore erosion with the offshore sedimentation, getting the whole picture together. I was just wondering about with the river profiles with the neck points migrating up the rivers. Does the geology make a difference about how quickly they migrate, or is it too small to worry about on that start?
So you are correct. The geology does make a difference. However, on continental length scales, it's more of a second order sensitivity. If we were looking at a particular river, then we would certainly need to take that into account. And there is work being done at Imperial at the moment that is looking at precisely that question.
Yep. At the beginning, you showed that really long seismic line.
Yeah.
And it was a bump which seemed to be over the continental ocean boundary.
Yeah.
And I was just wondering, whatever that structure is, was ponding up all these sediments being eroded down the rivers.
Let me just see if I can get this. Is it? Let's get this line up here.
That one.
Oh, that one. Yeah, I've seen it. Oh, here we go. Yeah. So you're talking about this. Yeah. So this looks like a swarm of sills in the seismic data. They're saucer shaped and look as though they're pretty diagnostic of igneous intrusions. I mean, that was actually something which I wanted to figure out what caused that, but there's no clear, I mean, within seismic data, you can't see any sort of feeder dikes or anything like that. So that was an open question that was left at the end of the PhD as to how that got there. It's actually kind of strange because you don't see any igneous activity anywhere else within the Mauritanian Basin itself. And
you normally get those sort of intrusions on the COVs.
Yeah, and west of that, you could see the Moho pretty clearly. So yeah, and this must have been recent because it's affected the. You can see the displacement of geology all the way to the seabed. So it must have been pretty recent. So in the region of subsidence, you're getting very localized eddies of uplift, which is very interesting.
Is that the Cape Verde Islands? Where would they be on that?
So the Cape Verde Islands are to the west of this, so beyond this line. So this line goes pretty much to the halfway point between the West African mainland and the Cape Verde Islands. So on this figure here, I've plotted it all together. Yeah, so the Cape Verde Islands are here. So that seismic line goes from here to there where the end of the circles are. So yeah, the Cape Verde Islands are further along. I think there's one question by Alexi that says, what is the resolution of the shear wave models? So the resolution, I think, this is work that I did in collaboration with the University of Leicester, was, if I'm not mistaken, was 250 kilometers by 250 kilometers, because it's a regional Africa-wide model for which we used the we just focused on this area. So yeah, I don't think there are any more questions online. Are there any more questions from you guys?
Well, something about the age of the rivers. I mean, you mentioned some of this uplift is fairly recent. So you can say about the defining of that and that appreciated based on the number of these tributaries. All the systems might be complex or have more nick points. Or
yeah. So one big caveat with all of this is the confidence at which we can use present day geomorphology to infer things from the past. So I've used throughout this presentation, the number 30 million years has come up again and again. And the reason for that is prior to that time, it isn't possible to confidently infer the positions of drainage divides and so on from present day geology. So when a large tectonic event happens, a big period of uplift or something, you will see if I go further into the present, if I go further along. So here it is. Yeah. So if we look at these profiles here, we can see that pretty much all of these river systems have tributaries that are grouped within a number of nick points. So looking at the Niger in particular, we can see 1, 2, 3, 4, 5 big nick points where lots of tributaries join the main river system. So these will be associated with specific periods of uplift and erosion that then caused rivers, the geomorphology to evolve and for smaller tributaries to join larger networks. And this is something which again is another avenue of research to actually be able to identify exactly which nick points along major river systems correspond to which geological events.
Is it linked to structural geology to some degree in that regard? So I usually work in things that are 1.5 billion cells.
Yeah.
30 million years like an air bus. But so generally, if you're looking at older continents, the river system morphology is generally defined by the geology.
Yeah.
And so prominent units, for example, versus
yeah.
versus
Yeah. So Yeah, definitely it will come into it. So I didn't look at that particular aspect within my PhD, but as I mentioned, this is an area of active research, and is also linked to provenance analysis as well, looking at how does riverbed geology basically affect drainage evolution. So yeah, that is definitely something which does play a factor in it, although it wasn't something which I had the time to look at in my research.
Do that for 18,000 rivers.
No. There is a paper published by my PhD supervisor Gareth Roberts, where he looks at Australian rivers. I think it was published in 2014 or something like that. So he actually looks at rivers using this methodology to calculate the uplift rate for continental Australia. So it's the question of how far back in time can you take this depends on how far back in time can you be confident that present day drainage is representative of what was going on. So in the case of Africa, that number is about 30 million years, because prior to that, well, large parts of Northern Africa were below sea level. And a lot of the drainage that has developed since then has been caused by uplift from that point. But whereas in the case of Australia, so I haven't studied Australia from a drainage point. Yeah. So if for Australia has been stable for a long time, for most of time, to be honest. Yeah, this could be taken back a long time.
So the drip of mantle plumes, they cause doming.
Yeah.
And then when the heat dissipates, they sink back.
Mm.
You know, the magma or whatever cools, becomes denser and sinks back
Yeah.
into the earth. And often there's a sedimentary basin formed over mantle plume.
Yeah, you're absolutely right. In Africa, that hasn't happened yet because the regions of uplift are still uplifting.
Yeah.
So the African superswell is an active event. You know, the southern half of Africa is currently being uplifted. The Mauritanian Basin is currently still subsiding. And along the west coast of Africa, where we see that uplift, those areas are still uplifting as well. But in the case of somewhere like Australia, which is, of course, it's much older cratonic crust, you'll have regions which have uplifted then since subsided. Yep.
Just one more suggestion. That bump that Peter was talking about in the seismic profile around the continent ocean boundary, could that be serpentinized mantle coming up as a diaphragm?
Absolutely, yeah. I think that is one. Yeah, that's a good point actually. It's not something which I focused on, but I'd be very interested to go back to that, hopefully to answer that question maybe one day. I scratched my head about that actually for a long time, but then my supervisor told me focus on the goal. You know, it was one of those things, because the whole idea of geodynamics was different to the original project brief as it was, and it kind of just came about from what the data told. Maybe I'd be up for that. Yeah.
I think it's wise words from your supervisor. So I haven't had a chance to people that want what's going to be a PhD. So that's pretty good stuff. Shall we let him off the hook now?
Cool.
Well, thank you. It was a great talk.